Welcome back to the next session and the last session of this chapter, Electrostatics. Friends, in the previous discussion, we had two applications of Gauss's law: electric field due to uniformly charged infinitely long straight conductor and uniformly charged infinite plane sheet. Now we are heading to the next concept, that is third application and the last application of this chapter, that is electric field due to uniformly charged spherical shell. So here I have considered a shell or a spherical shell of radii capital R, which is positively charged Q, having a surface charge density sigma. Now, in order to calculate the electric field due to this spherical shell, first and foremost we have to consider the Gaussian surface. In order to calculate the Gaussian surface, there is an important topic, the important concept in this heading is, since the charges are positive or the positive charges are there accumulated on the surface of the spherical shell, then the electric field is radially outward at all the directions of this sphere, because it is symmetric, spherically symmetric. Hence, we can calculate, it is possible to calculate the electric field at a distance of, say, any distance from the center O of the spherical shell. Time being, I want to calculate what is the electric field outside the spherical shell, that is case number 1, on the shell at this point and inside the cell. So that means, so in the third application, basically we are studying three important cases. So now let us go with the case 1. What case 1 says? So the case 1 says that it is the point P, if point P lies outside the spherical shell, outside the shell. So now first case is, so we are calculating the electric field at outside the spherical shell. Again, how to describe the diagram? Consider an uniformly charged spherical shell of radii capital R, which is spherically, it has spherical symmetric in nature. Then we want to calculate the electric field outside the spherical shell, and that itself is considered as one more Gaussian surface. Now I will draw the Gaussian surface outside, since it is sphere, so Gaussian surface also in the sphere form itself. So now it's sphere. I want to calculate the electric field at a point, say now P here. Point P lies here at a distance of R from the center of the spherical sphere O, then OP is equal to small r. Again, again same routine as we did in the previous section. So we consider sphere is the Gaussian surface in our case. Once we consider sphere as a Gaussian surface in our case, then I have to write the electric flux equation due to the Gaussian surface. Electric flux due to Gaussian surface is phi E is equal to E into delta S into cos theta. Since theta is equal to 0 here, 0 degree, because the electric field and the area vector both are in the same, having same magnitude and having the same direction, hence theta becomes 0. Then E into 4 pi r square, because cos 0 is 1, so it becomes 4 pi r square. So phi E is equal to 4 pi r square. Say equation number 1. After writing this part, then let's go to the next, that is electric flux due to Gauss's law. So if we write the electric flux due to the Gauss's law, then I'll get phi E is equal to Q by epsilon naught. Say equation number 2. From 1 and 2, again compare 1 and 2. Here no need to substitute for the electric flux equation, so that is surface charge density, just keep it as a Q by epsilon only. Then compare 1 and 2, then if you compare 1 and 2, then we will get E into 4 pi r square is equal to q by epsilon naught, then E is equal to 1 by 4 pi epsilon naught into q by r square. And if we express it vector form, vector E is equal to 1 by 4 pi epsilon naught into q by r square into r cap. So this is the final expression if the electric point P lies outside the spherical shell. Similarly, if the point P, if I bring this point P on the surface of the spherical shell, so same thing we are writing, just replacing this small r, that is small r radial distance small r by capital R, then if the point P lies, that is case 2, I will write here only. Now if the point case 2 on the shell, if the point P lies on the shell, then this R becomes capital R, because the sphere itself is a Gaussian surface. Then delta E is equal to phi is equal to A delta S cos theta, phi is equal to E into 4 pi r square. Just I am replacing this radial vector by another R, capital R square. So this side is same, again electric flux due to the Gauss's law same. Then this becomes R square. R square is equal to E 4 pi r square equal to q by epsilon naught, and this goes, again this becomes R square, then this becomes R square into R cap, or you can write even capital R cap also, so no need to worry about this. So just this is again if the point P lies on the shell. Suppose if I go to case 3, again case 3 is very important, inside the cell. So now we'll write case 3 here itself. Case 3, inside the shell. Inside the shell. Suppose if this point P, instead of lying outside the shell, on the cell, if the point P lies inside the cell, then what will be the electric flux equation? What is the electric field due to it? Then if you write the electric field, consider a point P inside the spherical shell, then that we have to write. Then write the electric flux equation, electric flux due to Gaussian surface, phi equal to E delta S cos theta, E into pi r square. But a problem comes here, when we are writing the electric flux equation, the charges are only accumulating on the surface of the sphere or any body, but not inside the body. The electric charges are accumulating only on the surface, not inside. Hence, here the electric charge enclosed by the surface is 0. That is, Q is equal to 0. If Q is 0, if there is no charge, there is no electric field. I can write directly E is equal to 0. That means if electric field is there, then it must be outside and on the cell. There is no electric field inside the cell because the charges are not enclosed by the surface inside it. So that is why no electric charges are enclosed by the surface 0. Hence Q equal to 0. If C equal to 0, electric field becomes 0. This is application number 3. And in the examination, the examiner may be interested in any two of the special cases. So he may ask, state Gauss's law in electrostatics, and hence there are an electric field due to uniformly charged spherical shell. He may ask, then you have to write all 3 special cases. Suppose if he asks, state Gauss's law in electrostatic, hence there are electric field outside or on the shell, hence write the electric field due to the electric inside the cell, means you have to write only this part. So he may ask any two special cases or all 3 cases. So that is depending on his interest. So now with this we are completing the chapter 1 electrostatics. Thank you.